So we're going to look at what are called complex fractions, and the term complex here doesn't actually mean imaginary, not like complex conjugates. Okay, complex just meaning a fraction within a fraction. So there's two methods that we're going to look at, and I'm going to go through these examples. And in the first example, I'm going to apply both methods. And then after that, we'll pick one and then pick another and go back and forth. In the notes, if you look tonight, for all of the notes, I use both methods. So if you like one more than the other, stick with the one that works for you. Okay? But all the problems are solved with both methods, so you can take a look at them if you think one is easier than the other. So the first method, and we're going to read through it, but it's easier to see with an example, which we'll do in a second, is to find a common denominator of the major numerator. Now, to give you an idea of what I'm saying here, a complex fraction looks like this. It's like a fraction. These are numbers I'm just putting here. Okay, so like imagine, I'll do it this way, make it easier. That's what a complex fraction would traditionally look like, with some operation in between them. Okay, that's physically what's happening here. So when you look at these steps, think about that kind of a fraction. So find a common denominator of the major numerator. That means find a common denominator of these two denominators here. This is like the major numerator. This is the major denominator. Within each, you have a numerator, denominator, numerator, denominator. Now, then you find a common denominator of the major denominator. So find an LCD of these two. Figure it out. Find an LCD of these two. Multiply the overall numerator by this reciprocal of the overall denominator. So that means you're going to end up with one fraction up here now. So imagine you find a common denominator. You're going to get everything over some number. Over here, you're going to get everything over some number. These no longer exist. It's all over one fraction. Now, if you have a fraction over a fraction at this point, when you divide a fraction by fraction, you multiply by the reciprocal. That's what step 2 is saying. If you can get this into one fraction in the bottom and make this top into one fraction, you can multiply the top by the reciprocal of the bottom. Remembering that dividing by a fraction is multiplication by the reciprocal. And then simplify. The second method is going to take these 8 spots, find an LCD for all the fractions involved. So look at not only just 2 of them, look at all 4 of these spots that I'm circling. And find an LCD for all of them. And then multiply the top and bottom by that LCD. And everything will just cancel out. And you don't have to worry about another common denominator. Okay, I prefer the second method. When I was in high school, though, I learned the first method. I never even thought about the second way to do it. And then when I was reading a textbook, I started looking at that and I was like, oh, that's another way to do this. So I actually prefer this method. But this is the way that I had learned it initially. They both work. The first one is probably more traditional. Find a common denominator of both the top and the bottom. And then you see that you're dividing by a fraction, so you multiply by the reciprocal. Here, it's a little bit different. You find an LCD of all 4 and multiply top and bottom through by that LCD, and everything cancels. And the first time you do it, you're like, oh, wow, that's pretty cool that they all cancel. Okay? So let's take a look at this now. For example 1. We got 4 denominators. So let's apply method 1 first. Method 1 is to find an LCD in the numerator, the major numerator. So look, and I'm going to circle it. Look up here. Okay, look up here. Find the least common denominator for this. Between 6 and 3, what's the LCD?
3. Oh, wait.
An LCD? What should I multiply the 3 by to make it look like the other one?
2.
Yeah, there we go, 2. Okay, so, but the LCD itself is 6 then, right? 3 times 2 gives us 6. So we multiply that one by 2 and that one by 2. On the bottom, what do I do? To find an LCD in the bottom fraction,
Multiply x over 5 by 2.
Yeah. Multiply this by 2. Now, as a result, that makes the overall numerator an LCD of 6. The overall denominator has an LCD of 10. So in the numerator, I get x minus 2x over 6 all over 2x minus 7 over 10. Now, this is method 1. And guys, we're doing a very easy problem right now on purpose. I made the denominators integers instead of expressions, because I want you to see the technique first, and then we'll apply it to expressions. So now I've got 2 fractions. What does step 2 say to do? Ben, what do I do next?
We have to multiply overall numerator by the reciprocal of the overall denominator.
Yeah, so take this, I'm calling it overall numerator because we have multiple numerators. Take the upper numerator, multiply by the reciprocal of the denominator. What's going to happen? We're going to see things start to cancel out. We're going to be able to reduce. Let's do it. X minus 2x, I'm going to write as negative x over 6. Multiplied by 10 over 2x minus 7. The 10 over 6 reduces to 5/3. Cancel, make that a 5. Cancel, make that a 3. Okay? And that's as far as I can go. I'll leave my final answer up here. I can distribute that out if I wanted to, right? But is it going to do anything there? I can't cancel a negative 5x. Those are factors up top. The bottom, we clearly don't have factors that reduce with that. Now, take the second technique and apply it to this problem. So let's rewrite the original below this. So the original I'm going to rewrite, okay? X over 6 minus x over 3 all over x over 5 minus 7/10. Look for an LCD of all four denominators.
30?
30. 6, 3, 5, and 10 all go into 30. They don't all go into 15. That would be the other one I was thinking. 6 and 10 don't go into 15. Let's make them all 30. Now, if I think they're all 30, the second step tells me to multiply the top and bottom by this LCD. So let's put a 30 here and a 30 here. Let's go ahead and put parentheses around the top and bottom now to remind ourselves that we're distributing this 30. And when we distribute this 30 to each term, what's going to happen is we're going to see some cancellations. 30 over 6 reduces to 5x. 30 over 3 reduces to 10x. 30 over 5 reduces to 6x. And finally, 30 distributed here over this 10 makes it a 3 times 7, which makes this a 21. So distribute the 30 to everything, and you'll see all the cancellations occur. So distributing here, I get 30x over 6, which is just 5x. Distributing here, I get 30x over 3, which is just 10x. Distributing in the denominator, I'm going to get 30x over 5, which is 6x. And finally, I'm going to get 30 times 7 over 10, which is really 3 times 7, or 21. This becomes negative 5x over 6x minus 21. Same answer, just factor out a 3. Okay, if you factor out a 3, you're going to have the 2x minus 7 in the bottom. It's the exact same answer we got a moment ago. Okay? Now, honestly, which method, just a quick show of hands, seemed easier to you? And you don't have to choose one way because I chose. Seriously, just pick your own. Who thought the first one seemed easier? Who thought the second one seemed easier? I honestly do think the second one is a little easier, but does it make sense how it works? Because last year I taught the second one, and only the second one. And some students definitely struggled with it. For some reason, when they would distribute the 30, they would forget to distribute to both terms or not cancel right. So use this technique and use this sample to remind yourself when you're doing your homework. Okay, and for this next example. So let's take the second method as an approach for the second example here. So now, see, this is what I'm saying. This is why it gets a little trickier now. To find an LCD of this, we can clearly see that x plus 5 is in some of the denominators and x minus 3 is in some of the denominators. So we need both of them to be in all of the denominators to get an LCD, really. So what would the LCD be in this problem of the overall fraction?
X plus 15.
Not x plus 15. If I had, ready? If I had denominators like as the following. Let's say I had this. Now, what would the least common denominator of that fraction be for all those denominators? Because you did 2 times 3, didn't you? So what should it be for this one?
15.
Not negative 15. Guys, there's x's in there. You can't just ignore the x's. Ben? Not x minus 15.
X plus 15 over X plus
No.
Can you just do x plus 5 times x minus 3?
Yes? You're all overthinking it. It's a simple approach. Niall, how did you get 6? What did you do?
Multiply 2 and 3.
So you multiply x plus 5 times the quantity x minus 3. So it is whatever you see there. When you have factors, and those factors are not common amongst, think about it, maybe it'd help you to do this. Mentally put parentheses around all your denominators. Now do you see how those are all individual factors there? You have to have x plus 5, x minus 3 in all of the denominators to get a least common denominator of everything. And that's what method 2 approach is. So method 2 is easy when they're numbers, right? Like we did a minute ago. But when it's not numbers, you need to consider the fact that if you don't have things in common in those denominators, if they're not factorable, you need to just multiply those denominators by each other. Well, I don't care about the bottom right denominator, the x plus 5 that you're seeing down here, because it's the same as this x plus 5. So the product of this and this is the same thing as Niall did. 2 times 3 gave us 6. That's where he came up with this common denominator of this. So the common denominator is x plus 5 times the quantity x minus 3.
X squared plus 2x minus 15.
Are you giving me the...
Yeah.
So we don't need to do that though. We don't need to multiply it out. Let me explain why. That's okay, Ryan. Let me explain why we don't have to multiply it out, and there's a reason. So let's multiply the top and bottom by the LCD we just mentioned. Now, put parentheses around the major denominator. So you remember you need to distribute this whole thing. Do the numerator first, please. Forget the denominator of the whole thing. Okay, so if you have to cover it up, cover it up. Look up here only. Distribute both of these. Okay, take this entire thing, this entire product, and put it in the numerator up here. Again, take the entire product, put it in the numerator. What's going to cancel? What's going to cancel if you take this whole thing and multiply it, so as a result, putting it in the numerators when you multiply? Charles, what cancels?
X plus 5.
X plus 5 cancels. Again, when you multiply something, it means you multiply it by the numerator. So technically, I could just do this. And I know it's difficult at first, but we're going to do this over and over. And forget that this is even here. Just put it up there. And as a result, and that's what multiplication is, you put something in the numerator of a fraction, means multiply. If it was derived, you put it in the denominator. These cancel, giving you 3 times x minus 3. You have to pause and ask questions if that doesn't make sense. Or ask me something that seems confusing about that. Because we're going to do this again. Niall.
I don't like how it went on, but I don't know. Like what, I don't know.
Alright, so how about this? Let's take a different approach real quick. Hold on. What if I wrote each of these over 1? Like that. Does that make sense that this would multiply by the top and this would multiply by the bottom? If I had two fractions and I was multiplying them, how do you multiply fractions? What do you do when you multiply fractions? Multiply across. Multiply the tops, multiply the bottoms. This is the top times this. This 1 here is the bottom of the fraction
Oh, okay, yeah.
times this here. So as a result, when I multiply this whole thing right here, it kind of just goes in the numerator. So instead, I'm kind of like taking this whole thing, just putting it in the numerator up here. And I'm seeing that the x plus 5 is canceled, right?
Yeah.
So left behind this 3 and this x minus 3. That goes here and here. Now in the bottom, when I do this, this is where it gets tricky. I'm going to have to distribute this to this numerator and this numerator. Look where I'm pointing, please. I have to distribute this entire thing to this numerator, so I have to put it in this numerator and put it in this numerator. Well, when I put it in this numerator over here, keep looking at the board, please. When I put it in this numerator here, it's the same thing as this here. The x plus 5s would cancel again, right? When I put it in this numerator, what cancels? X minus 3. So pick up on the trend. I don't want to rewrite this like this every time. Do you follow what I'm saying? I don't want to do this every time, but I'm going to do it this time. So I take this whole thing, and I'm going to put it in this numerator. I'm going to write it down here, so we can see what it looks like. And that's over the quantity x minus 3. I'm just rewriting the denominator here. And then the other one is plus 1. Can I erase this still? Can I move it maybe? No. Awesome. It's going to be 1 times x plus 5, x minus 3, over x plus 5. Now I don't want to do this every time I do these problems. But to show you this time, cancel, 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 cancel. This part here, that I'm circling, gets put down here. Because remember, that's taking the place of this right here. This portion, this 1 times x minus 3, is simply, simply x minus 3 here. And that comes about from this right here. So this result at the bottom here is what we're really counting on. It got rid of all the denominators. So method 2 seems easy with numbers. But I want to show you here how it's not as easy when you have variables involved. Method 1 is the same though. Method 1 is more difficult with variables as well. But the concept again is what? You want to find something that has the same factors in the denominators. So if you have binomials, binomials are factors. Kelly, you had a hand up at one point. You sure? Okay. Things cleared up? All right. So I've got 3x minus 9 over 2x plus 10 plus x minus 3. The only reason I'm doing this, I could actually leave the numerator if I wanted to. But the denominator I should, because I could simplify possibly. So again, I should really just leave the numerator for now. The denominator becomes 3x plus 7. So unfortunately, the denominator does not cancel. It doesn't reduce, because I can't factor 3 out. Or I can't factor anything out to leave me behind with an x minus 3. Okay? Now, if you take method 1 approach, you'll get the same answer. It will also be a little more difficult than the other method was, or than method 1 was, with the example with only numbers involved. Okay? Now, give me your opinion. Do you want to try method 1 on this one, or do you want to go on to another question and do method 2 again and see how that looks with the second question? Hands for trying method 1 on this problem. Going on to the next problem with method 2. Okay, that's fine. So let's take a look at the next example. So the next example looks tricky because it looks like some of our terms don't have denominators. Right? You see the ones there? The ones don't have denominators, but if there's no denominator there, what's the denominator really? 1. Always remember that. If there's no denominator, it's really a 1. Well, one of our denominators has an x. Another denominator has x times x, or x squared. So it looks like the things that are over x, like this right here, this 3 over x and this 2 over x, what do they need? What do they need to have the same denominator? What would they really need? Another x, really. This one would need an x squared in it, wouldn't it? But the overall common denominator of all these denominators would be what? X squared. We don't have to go cubed. Because squared's already in this one. Just multiply this times x over x to make this x squared. Multiply this times x squared times x over x squared to make that denominator x squared. Why go up to x cubed, right? Because x is a factor of x squared. So remember how in the last example we multiplied our denominators? Here we don't have to multiply our denominators. If we do that, we will get x cubed, right? But we don't have to. Just make it x squared because remember, x squared is already x times x. So let's multiply by x squared over x squared. Remembering to do this every time. What does that remind me to do? Distribute. Distribute. So distributing x squared to 1 makes it just x squared. Distributing x squared to 3 over x makes it 3x squared over x, which is just 3x. If it helps you, honestly, just write it up here. Okay? And then in the next one, write it up here. And then you can get rid of this. So if you want to write it in all different little spots, do it. And then cancel the 3x squared over x to become 3x. Then the x squared is canceled, leaving behind what on the end? A 2. How about the denominator? The denominator. Ryan, what do you get for the denominator when you distribute x squared? For both. What's the overall denominator become? Distributing the x squared to both of those terms.
Those to those.
Yeah, so start distributing this to this.
We need, x squared plus 2x.
Plus 2x. Very good. Okay, so what we notice here is that the top looks like a quadratic we can factor. The bottom, we can take out a GCF. What's the GCF in the bottom? X. Leave behind x plus 2. Now, that's the easy one to factor. There's a good chance the numerator has an x plus 2, isn't there? A lot of these problems on like SAT type tests, what happens? They cancel. This is a perfect SAT problem. Complex fractions is on like every single SAT. Anything with rational expressions is on the SAT. This section 5.6 through 5.9 is really important. Okay, you're going to see that a lot. Numerator factors into what? Yeah. And we see the x plus 2 cancellation, leaving our answer as x plus 1 over x. Now, you could write it that way, or how else could you write it? How else could you write it? Divide the denominator, right, into both terms in the numerator. What would that give you? Okay, a very common expression in finance. 1 plus like 1 over n. Okay, it has to do with the definition of a constant called e, which is similar like pi. Okay, an irrational constant. It's called the natural logarithm. No, natural base of the logarithm. So just divide the x over x to give you 1, and then 1 over x is 1 over x. Very common for the SAT to see either expression as the answer. All right, example 4. We've got something that looks really annoying at first. But think about the definition of a negative exponent.
Just make everything under all of those terms are denominator under 1.
Very good. And make them what?
1 over r cubed.
So instead of negative, make them
Positive.
perfect, Niall. Exactly what he said. Put them all in the denominator with a 1 in the numerator and make them negative. Why would I do that? Why would I do that? Or why would Niall do that? Because he's right. But why? It makes it easier and makes it look like a complex fraction. So now I know I can figure out what my LCD is. Okay? I clearly see that I've got at least r cubed in one of them, at least s cubed in another one of them. So I need both of those things in the overall denominator of the whole thing. Well, this r is already in this. Do we all see what I'm saying when I say that? Let me point again. Take a look. This r is already in this. Because this is really r times r times r. So this r is embedded in here already. So I don't even care about this denominator because it's already a part of this one. So I need this and I need this. So my overall least common denominator is the product of what I need. I need these in both, in all, to get a common denominator. So the product of these two is my common denominator. Okay, again, not an easy one to look at. So let's multiply everything by r cubed s cubed over r cubed s cubed. Now remind yourself, this is really over 1. This is really over 1. That might help you in this process. Okay, and we are multiplying. If that helps you do that, please put them over 1. I think that might be very useful this year, because I think that really threw some people off. And they didn't recognize that r cubed s cubed is really a fraction over 1. And when you multiply fraction by fraction, you just put that r cubed s cubed in all the numerators. Just literally take r cubed s cubed, put it in all 4 numerators, and reduce accordingly. So again, if it helps you, do this. And then cross these off if it helps. Okay, just put r cubed, s cubed in all of them and reduce accordingly. R cubed cancels here, s cubed cancels over here. Over here, r makes this r squared now, and this s canceling makes this s squared. Making the overall fraction s cubed plus r cubed. Again, remembering because these canceled and these canceled, what I'm circling up there. the denominator becomes r squared s cubed plus r cubed s squared. Because again, cancellation. Now, it might seem like you're done, and you might want to stop at this problem. But believe it or not, you can go a little bit further. What can you do? Which is not always obvious here.
Oh, you take out r squared s squared from the bottom, and then you get r s plus r, and then you can take out one of make the top s squared plus r squared over r squared s squared.
Very close. The denominator is exactly right. Look at the denominator. R squared, S squared, R squared, S squared is in both of these. The cube just makes a little bit more, but we'll leave that behind. So if I take out an R squared, there's none of that left. I take out R squared out of S cubed, it leaves behind with an S. So I'll put that S right here. Then I take R squared, S squared out of this, leaves behind one R. Now the numerator is a different kind of factoring. The numerator is what kind of factoring? It's a special technique we learned. Even if you don't know how to do it, try to give me the name of what it's called. There's a plus sign. In math, that means what? What's the word that represents plus? Sum. There it is. Sum of cubes. Remember, this is s plus r times s squared minus sr plus r squared. That's the factoring technique for sum of cubes. Okay, for sum of cubes. One of the few that you really need to remember for this. What cancels as a result? Cal? S plus R cancels. So my final answer, and I know I can't factor the numerator because the quadratic that you get when you do difference or sum of cubes is never factorable. So I cannot factor the remainder of that numerator. Okay? Again, not obvious, a very difficult problem. I don't think the SAT needs you to memorize sum or difference of cubes. Okay? On your final, if there's a sum or difference of cubes problems, there's probably only one of them. So just try to memorize the formula. That's all you really need to do. Okay? Let's see. All right, example 5. Let's finish off with one that makes us think a little bit. And we've seen something like this before. We've seen these problems where I tell you, evaluate the expression f of, and then it's like x plus 7. You have to put x plus 7 into all the spots where you had an x originally. Well, this is f of x. What does that mean? How can you have f of x?
Find f of x and then try to do it again.
Yeah. So if this had said f of 2, you would take a 2 and plug it in here and here, right? That's obvious. We've done that many times now. That's simple. So you need to take f of x, the overall function, which is defined as x plus 1, x over x plus 1. You need to take that whole thing, x over x plus 1, and plug it in up here and over here. So you're taking the function and plugging it into itself. It's a technique that you're going to have to use in calculus. So I thought I'd do this problem. We don't need calculus to do this, but we can at least evaluate a function of itself. Okay? So take x over x plus 1 and plug it into those two locations. So x over x plus 1 goes in the overall numerator. X over x plus 1 goes here. And then we just have a remaining plus 1 there. So we're literally taking the quantity f of x and plugging it into f of x. It's like f of g of x. If you had another function, you would take that whole function and plug it in those two spots. Well, here's that whole other function right here. We plug it in those two spots. But it happens to be the same function. So here's our fraction now. And we can clearly see now that we have a complex fraction. What's my overall least common denominator? Be careful here. It's just x plus 1. Okay? Because this 1 is really 1 over 1. And again, if it helps you, write this fraction that way. And you can clearly see that we need an x plus 1 in this denominator over here to enable us to have a common denominator of the whole thing. So as a result, and again, I don't really need that there, I multiply by x plus 1 over x plus 1. If I remind myself that this is over 1, again, that's okay. And then I go ahead and distribute. When I distribute to the numerator, what's left behind? I get x times x plus 1 over x plus 1. So what's left behind from that numerator up top? Mike, what do you got? What's left behind in the numerator? When I distribute this over here, what happens? It's what? X squared plus x is fine, but don't even distribute it. Just take this x plus 1, right? Place it in the numerator. What would happen to it? Yeah. Not x plus 1. Do this, right? Put it up here. And then what happens?
Oh, it's just 1.
Not just 1. You're almost there.
X.
So you take it, you place it in the numerator. You take this 1, you place the 1 in the denominator. And you recognize that the x plus 1's cancel, right? So all you're left with is x. Okay? So when you're canceling those two, you're left behind with just the x. What about the denominator? How about the denominator? Ben, what about the denominator? Tell me what to do with this.
Just distribute.
Okay, when I distribute it over there, I'm really just putting x plus 1 up here with this, right? So what happens? With this, right? Leaving behind what? Okay, just x. And then distributing it here, what do I do?
You get x plus 1.
Which is just x plus 1. Okay, very good, Ben. So the denominator, I can, combine like terms. And there's my final answer. That's what f of x is. Let's do one more example. I just want to go over the least common denominator because I think I need to add one more example to the notes. Because in the homework, you're going to have one of this, okay? Let's say we've got, here's the overall fraction. Here's the numerator is going to be 1 fraction. The denominator will be 2. Let's say we've got 2x over x squared plus 5x plus 6 over x plus 3 minus 2 over x minus 4. Actually, I'm going to make this left denominator a 5. Left numerator of the denominator. All right. As a result, what can I do to start this problem? Because I think on the homework I had a few of these, and we didn't really do one exactly like this, but you should recognize something to start with. Kelly. Factor out the quadratic portion, absolutely. So the portion that's a quadratic we should factor out. So that x squared plus 5x plus 6 right here, factor it. So it makes this easier. What does that become when I factor it? Right? X plus 3, x plus 2. Don't rewrite the whole problem. Just literally do this, okay? Make it easier on yourself. Because you don't have to factor the other ones. They're already done. Now, how many different factors do I have in these denominators? How many different ones? 3. X plus 3, x plus 2, x minus 4. The x plus 3 repeats itself. Great. That's awesome. But it doesn't really mean anything. It repeats itself. So what? Okay? So as a result, that means that I need to multiply both the top and bottom by the overall LCD, which is the product of all the factors always, right? Remember, the LCD is the product of all the factors. Since there's 3 factors, the LCD is a triple product. So we have to multiply the top and bottom by the quantity x plus 3, x plus 2, x minus 4, all over. X plus 3, x plus 2, and x minus 4. If you want to put that over 1, if it helps you, again, it's fine. Parentheses around this to remind myself, and I'm distributing this overall thing. Okay, does that make sense what I'm doing here? What does the numerator become, Niall? And you don't have to give me you can leave it in factored form. Cancel things in the numerator, though. What does that become when you make some cancellations in the numerator?
X minus 4. 2x squared. No.
Write it as factors. It's fine. 2x.
2x times quantity of x minus 4.
Very good. Okay, now again, look, because this cancels with this when you're multiplying. That's obvious in the numerator because you're multiplying two fractions, so you diagonally cancel. You've done that before. It's very simple. The denominator, though, you have to remind yourself that you're really taking these three terms, these three factors, and putting them in both numerators. So the x plus 3 will cancel with the left fraction, leaving behind a 5, and then x plus 2, x minus 4. Then the x minus, and I'm going to put a minus sign, put a big bracket here, remember that I'm subtracting this whole thing. Then the x minus 4 will cancel with this one. I can cross it off now because now I don't care what I see. And I have 2 times x plus 3, x plus 2. Okay, and this is my overall answer. Obviously, I would come up with a quadratic for both of these denominators, come up with an overall simplified quadratic, right? Combine all my like terms, multiply everything out over here, multiply everything out over here, subtract this whole polynomial from this one, come up with an overall quadratic, try and factor it, and if it could factor and possibly cancel with one of these two factors, I would do that. We're going to run out of time. That's why I'm telling you what I would do. Does that make sense? Okay, so this whole technique is about always thinking about list all the factors of all the denominators, and that's what you're going to multiply by over here on the right-hand side. Perfect. I want you to be ready for a quiz on Descartes' rule signs and yesterday's homework. Okay, so make sure that if you have time today during a free, try and get this homework done. I'd rather you be ready for the quiz and take another day on the homework and just take a 4.5 if you run out of time. Okay?